All right, this is the answer key video for the topic 6.5 practice problems on the energy of phase changes. All right, so again, we've talked about phase changes before, right, when we were doing our review stuff back in first semester, okay, but now we're really talking about the energy required, okay, and again, the energy is all that we've been talking about in this unit, okay, so a couple main things here. Okay, I think we really need to understand what this graph is, okay, and it is our heat versus temperature graph, okay, and so again, if we take a second and really look at what this is saying, okay, we're going to start as a solid, all right, and as we add more heat, we're raising the temperature of that solid until we get to the melting point of that solid. Then, as we continue to add heat, the temperature doesn't change because all of that heat that is being added or being absorbed is being used to break the IMFs in order for us to go from a solid to a liquid. Okay, so essentially all the heat is being used right here for melting, which is why the temperature hasn't gone up. Then as soon as we are all liquid, okay, when we add more heat, we are now raising the temperature of that liquid until we reach the boiling point. Then again, what you can notice here is as we add more heat, the temperature isn't changing because all that heat is going towards boiling or breaking the IMFs between the molecules that make it a liquid instead of a gas. All right, at this point, we've broken all of the IMFs and we are totally just a gas. So as we add more heat, the temperature will continue to rise. Okay, so again, heating, and we can go in the other direction, making it cooling. All right, but what you're going to notice here is a couple things. Again, you're always going to have plateaus. All right, the plateau of boiling, right? The plateau of boiling is going to be larger than that of melting because going from a solid to a liquid, we have to break some IMFs, right? Intermolecular forces. But going from a liquid to a gas, we have to break all of them. All right, we have to break all of the IMFs. All right, therefore, it's going to require a lot more heat, which is why this plateau is much, much larger. Okay, so if we're going from left to right, that makes it endothermic because obviously we're absorbing heat. If we are going the opposite direction, that would make it exothermic because we are releasing heat or giving heat up. Okay, so along with this graph here, we have to be comfortable with these terms. Okay, going from a solid to a liquid is melting, liquid to a gas is boiling or vaporization. All right, in the other direction, gas to liquid is condensation, liquid to solid is freezing, fusion, or crystallization. Now, the main ones that we'll use is fusion and vaporization. Okay, we'll use fusion and vaporization a whole lot. All right, so right here, that is also known as the H of fusion. All right, and up here is the vaporization. Okay, so those are very, very common, but we have to be familiar with all of these words here. All right, even the fact that going from a solid to a gas is called sublimation, and going from a gas to a solid is called deposition. All right, then throughout all of these phase changes, okay, we can use this equation, or technically these two equations. However, they are saying the same thing. Q is equal to M delta H, okay? That's if we have the mass, right? So that would be 1, or we use the exact same equation, but instead of doing mass, we now have the moles, okay? So what that's going to depend on when you use M versus M is your units on H. Okay, so if it is something per mole, then you're going to use the moles. If it's something per grams, you're going to use the mass. Okay, so again, really paying attention to units here. All right, so if we look at number 1, or the I do problem, okay, again, heat of fusion is much smaller than my heat of vaporization. All right, given the heating curve for mercury, calculate the heat to freeze 100 grams of mercury. So we're talking about right here. Okay, so we have M delta H, okay, because we're given our 100 grams. However, if we look at these values here, this is kilojoules per mole. Okay, so the first thing we have to do here And that's what that is the conversion to moles. All right, that is our conversion to moles. And again, how do we do it? We multiply by our grams by our molar mass, okay, in the units of 1 mole per some number of grams, okay? Then from there, we just take that value, our delta heat of fusion, and we multiply, because what's going to happen is grams will cancel with grams, moles will cancel with moles, and we're left with kilojoules. All right, so again, heat is in units of joules or kilojoules. All right, and the final thing I need you to notice here is this is negative, okay, negative, because we are freezing, so we're going in the opposite direction, okay, and it should make a little bit of sense to you because going from a liquid to a solid means it is exothermic. We have to give off heat, so that should be a negative value, okay, so it should be negative because it's exothermic. All right, you flip the sign. All right, if we were going from a solid to a liquid, we would just use that value in the positive direction because obviously we need to absorb that much heat. All right, we do problem, of course, please make sure you're watching that. Next one here, all right, the you do problems, okay? Point where there's only a gas present. That would be at F. Okay, E is not the correct answer because at E, we still have the conversion of some going to some being liquids trying to go to gases. Okay, so we only have gases at point F. All right, then temperature at which vaporization occurs. Okay, so there's a lot of things here. It says first off, figure out where vaporization is. All right, and that is up here. We follow that across 700, and then finally the unit comes from our axes, Kelvin. All right. C, point where a mixture of a solid and a liquid are present. Okay. So that would happen at point B and at point C, anywhere along that plateau. Because again, the plateau is occurring because all of the heat being added or absorbed is being used to convert from one thing to the next. All right. D, points where a gas turns into a liquid. All right. A gas turns into a liquid. So again, that means we're going in the opposite direction from point E to point D. All right. Point E to point D. Again, you got to be really careful with what you're being asked. It's not liquid to a gas, which would be D to E. It's gas to a liquid. All right. E, temperature at which the substance starts to freeze. So again, that's also the temperature at which the substance starts to melt, depending on the way that you're looking at it. So again, we're looking at this plateau right here, 200 Kelvin. All right. Then the last one, range where there is only a liquid. All right. So that would be the range between C and D. Okay. Not at point C or point D, right? Because at that point, conversions are still happening. But we're talking about this vertical line, this diagonal line here. All right. Then A, for number 2, calculate the amount of energy needed to boil. Okay. 91.2 grams of carbon tetrachloride at its boiling point, 350 Kelvin. Okay. It's giving you lots of extra information in this problem. All right. So the things that we need to pay attention to are how much grams we start with. Okay. And since it's in grams, and usually we do things in moles, this molar mass might come in play, especially considering the fact that both of these are in kilojoules per mole, okay? Now, this question here is asking you to think about which value do you need? Am I doing fusion or am I doing vaporization, okay? And we were doing vaporization, so we're going to use this value there, okay? Because obviously it says how much energy does it need to boil? Okay, to boil. All right. So we're going to start with what we're given and our main factor here. Okay, our 91.2 grams. Then we're going to turn that into moles. Because again, grams cancel with grams. I'm left with moles. All right, now I multiply and get our kilojoules. All right, so the equation we technically used here is Q is equal to N delta H, okay? But we had to convert into N from N, okay? But again, that's the equation we've been using a whole lot, okay? Then the last one here, draw a particulate level diagram to show this phase change. Okay, so before it boils means it's a liquid. All right, so you could clearly see that they're all kind of touching. All right, you could infer that there's IMS holding these close together. Then again, to when it's boiling, it should be a gas. All right, so whether or not you added the arrows, okay, is not a big deal. But what you need to have is that these particles are very far spread apart from each other. Again, they're free to move. We've now broken all IMFs, right? And they are now in the gaseous form. All right, number 3. The heat of fusion for water is 601 kilojoules per mole, and the heat of vaporization for water is that. How much energy is needed to melt? So again, starting with grams of ice, okay? Q equals M delta H. But both of my delta H values are in moles. So we need to convert from grams to moles, okay? So again, that's this first part. We're going from molar, oh my gosh, I'm so sorry. We are going from grams to moles using our molar mass, okay? Then we're going to multiply by one of those delta H values, all right? So again, how much energy is needed to melt, okay? So if we're melting things, we're talking about the heat of fusion, okay? We're talking about the heat of fusion, all right? So then we multiply by that 601. Moles cancel with moles. We're left with just kilojoules. All right. Then number 4, how much energy is needed to heat 36 grams of ice from negative 10.5 up to 22.5? All right. So lots of information here. Okay. So what I want to point you to is this diagram here. Okay. So if we look at this here, when we're at negative 10.5, okay, hopefully we understand that it says ice, which means it's a solid, okay? So it means it's a solid. Then we're going to heat it up till we get about 0, okay? At that point, we start going from a solid to a liquid, okay? Then the third point there is that we go and are just a liquid, and we just heat the liquid up to the 22.5, okay? So there is some basic information that you are expected to know here, that water heats, melts, right, at 1 degree Celsius, okay? And then it boils at 100 degrees Celsius, all right? So we're going to use our 2 main equations for this unit here. All right, and the reason we use one versus the other is when we have a change in temperature, okay? When we have a change in temperature. So here we have a change in temperature. So we're going to use Q equals MC delta T because there is a change in temperature. Same thing here with our just liquid heating. We're going to use Q equals MC delta T. All right. It is only when we do not have a change in temperature that we're going to use that equation there, our Q equals M delta H, okay? Our M delta H, all right? Then what I need to also point out to you is, again, you're given all the specific heat values. You obviously are not using the one for the gas, okay? So if we look at the first one, though, in the first phase of this, down here, phase 1, we are only a solid. So we're going to use the specific heat for the solid, okay? But it is Q equals MC delta T. And in this one, we don't need to convert from grams to moles because our unit for specific heat right here has the grams, okay? So that's going to cancel out our grams, all right? So we have 36 times our specific heat and our temperature change. And again, you have to infer this temperature change a little bit or a tiny bit there, okay? Because you have to know that it's going to melt at 0 degrees, okay? Then you can get your Q value in our unit of joules, all right? The second part, Q equals M delta H, all right? In this one, we do need to convert 2 moles. So that's that first part. That's going from M to N. So now we're in moles, okay? And then normally we would just have this value right there, okay? Our 6.01 kilojoules per mole. And where did that number come from? Up at the above. Okay, that is right here, the heat of fusion for water. Okay, then you could have stopped there and gotten your value in kilojoules, right? But at some point we would have to convert them all to the same unit, so I just did it right here in the one step. Okay, I went from kilojoules to joules. So first answer was in joules. I made my second answer into joules. Okay. All right, and then number 3 here. Q equals MC delta T again, because again, we'll have a change in temperature. Okay, so my same 36 grams, but now I'm using my specific heat for the liquid. Okay, grams cancel with grams. All right, my change in temperature is from my 0 to my 22.5. Okay, and that's going to cancel my degrees Celsius, so I'm left with just joules. Okay. Then the last part of this here is that you have to just add those 3 values together. Okay, so if you did not convert from the second equation, right, straight into kilojoules, you would have had a joule, a kilojoule, and a joule. Okay, so for this answer, you could have had your total in joules, or you could have had it in kilojoules. Does not matter to me, okay, and would not matter to AP as long as it's not explicitly stated that it has to be in some unit. Okay, so either one of those would be fine. All right. Then the last one here, naphthalene is a primary component of mothballs. Again, great, we add extra information. What you need to pay attention to is it readily sublimes, okay? And again, what does sublime mean? It means it goes from a solid to a gas, okay? Then it says the heat of sublimation is right here. So don't even necessarily need to know that because the heat of sublimation is given to us, okay? How much energy is needed to sublime 15 grams? Well, again, Q equals M delta H. However, this delta H value has moles, so we need to convert from from grams to moles, okay, using our molar mass, which is provided. So again, we go from mass to moles, and then multiply. So grams cancel with grams, moles cancel with moles. I'm left with just kilojoules, which is a unit of heat. Therefore, we are done. Okay? So I think, again, I'm going to reiterate, I think the main part of this that you have to really be comfortable with and understand is this top portion right here. Okay? That there is essentially one main equation that you're going to use. Okay? That you have to understand how this heating and cooling curve works. And then the basic terminology of phase changes. All right? If you have any questions, let me know. Otherwise, thanks, guys.